The universe is vast. It's mind-bogglingly, incomprehensibly huge. Our fastest spacecraft would take tens of thousands of years to reach the nearest star system. Imagine crossing the entire Milky Way, a journey of 100,000 light-years. That's a long road trip. Astronomers and dreamers ask, is there a shortcut? A secret passage through the cosmic fabric? Enter the wormhole. Sci-fi idea rooted in serious science, not fantasy, a theoretical possibility allowed by physics. Think of the universe as a crumpled piece of paper. To go from A to B, you crawl across the surface, the long way, or punch a hole through the paper. Go directly from start to finish. That's a wormhole, a tunnel, a bridge between distant points in space-time. Link two places in our galaxy, or connect to another universe entirely. The universe's express lane. This idea forces us to examine space and time. Is space empty nothingness, or is it real and physical? Bendable, stretchable, even tearable. Einstein suggests it's the latter. Space-time is a flexible fabric. A wormhole is an extreme warp, a dramatic topological tunnel. Let's explore these shortcuts. We'll look at where the idea came from, the physics that might support it, the huge challenges to using one. Let's get down to basics. What is a wormhole? Forget the flashy special effects from movies for a moment. At its core, a wormhole is a theoretical structure connecting two disparate points in space-time. The technical term is an Einstein-Rosen bridge. Imagine you have two separate cities on a map. You can drive the long, winding road between them, or you could build a bridge that goes straight across the valley. A wormhole is like that bridge, but instead of crossing a valley, it crosses the vast expanse of space-time. The structure of a wormhole is fascinating to think about. It would have at least two mouths, connected by a single throat. You would enter one mouth, travel through the throat, and exit the other mouth somewhere else entirely. That somewhere else could be just a few miles away, or it could be on the other side of the universe. It could even be a different point in time, leading to all sorts of paradoxes that give physicists headaches. This is because in Einstein's universe, space and time are woven together into a single entity called space-time. If you can build a bridge through space, the physics suggests you might also be able to build a bridge through time. This opens up the possibility of time travel, but it also comes with theoretical baggage, like the famous grandfather paradox. The story begins with Albert Einstein. In 1935, Einstein and his colleague Nathan Rosen were exploring the mathematics of general relativity. They discovered a solution to the equations that described a kind of bridge connecting two separate sheets of space-time. Then, in the 1950s, physicist John Wheeler, who coined the terms black hole and wormhole, began to explore these concepts more deeply. He imagined space-time at the smallest scales as a quantum foam, with tiny, fleeting wormholes popping in and out of existence. The next big leap came in the 1980s thanks to a request from astronomer Carl Sagan. Sagan was writing Contact and wanted a scientifically plausible way to travel across the galaxy, so he asked physicist Kip Thorne for help. Thorne's work revealed a major catch. To keep a wormhole's throat from collapsing, you'd need something very special, exotic matter. This isn't just rare matter, it's matter that seems to violate known physics. It would need anti-gravity, pushing space-time apart instead of pulling it together. The search for exotic matter, or ways to avoid needing it, has become a central focus of modern wormhole research. To truly grasp the concept of a wormhole, you have to understand Albert Einstein's revolutionary idea of space-time. Before Einstein, we thought of space as a fixed, unchanging stage. Time was a separate, universal clock. But Einstein's theory of general relativity, published in 1915, changed everything. He showed that space and time are interconnected, forming a four-dimensional fabric called space-time. Think of it like a trampoline. If you place a bowling ball in the center, the fabric sags. That dip mirrors how a massive object like the sun warps space-time. If a smaller marble rolls nearby, it follows the curve in the fabric created by the bowling ball. That's gravity in a nutshell. It's not a force, but the geometry of space-time. A black hole forms when so much mass is packed into a tiny space it warps space-time infinitely. Nothing, not even light, can escape that hole. The wormhole is a different extreme geometry. Instead of a single pit, two pits are connected, forming a tunnel. It's a topological bridge made from space-time itself. One mind-blowing fact that emerges from this is that gravity can affect time. This is gravitational time dilation. Time runs slower in stronger gravitational fields. A clock on Earth's surface ticks slightly slower than a clock on a satellite in orbit. This is experimentally verified. GPS needs this correction. For a wormhole, the time bending would be extreme. Traveling through one could land you at a different time than you left. So, what would it be like to actually see or travel through a wormhole? As you approach, it wouldn't look like a black hole but would appear as a sphere, like looking into a crystal ball. But this isn't just any sphere, it's a window to another place. Traveling through the throat, you'd be surrounded by exotic matter acting like a scaffold to prop it open. The throat could be just a few meters long. The trip could take mere seconds. You've crossed a galactic distance in less time than it takes to make a cup of coffee. It's incredible, but it all hinges on exotic matter. With all this incredible potential, the big question remains, where are all the wormholes? Theoretical wormholes are incredibly unstable. The moment they form, immense gravitational pull would cause their throat to collapse at the speed of light. To keep a wormhole open, you need exotic matter with negative energy density. All the matter and energy we've ever observed, stars, planets, dark matter, light, has positive energy density. We need something with repulsive gravity, and we have never found anything like it. Even if a stable wormhole did exist, finding it would be extremely difficult. A wormhole's mouth wouldn't emit light. It would be visible only by how it distorts light from stars and galaxies behind it. Astronomers are currently searching for these specific gravitational lensing signatures. Some scientists have proposed that supermassive objects at galaxy centers, which we believe to be black holes, could actually be wormhole mouths. The wormhole remains a beautiful mathematical idea that has not yet made the leap to physical reality. It's a solution to Einstein's equations. But not all mathematical solutions correspond to things that actually exist. The physics of quantum gravity, a theory we don't have yet that would unite general relativity and quantum mechanics, might hold the final answer. It could be that quantum gravity forbids stable wormholes, or it could reveal a natural way for them to form. Until then, the wormhole exists as a profound and tantalizing what-if. A testament to our unending curiosity and our desire to find a shortcut across the cosmic sea. The universe doesn't owe us sense, but asking big questions brings us closer to our place within it. Studying wormholes reveals bizarre secrets of the universe. It's about gravity, exotic matter, the fundamental structure of reality itself. Despite huge challenges, wormhole travel stays a serious scientific pursuit and a driver of human imagination, pushing the boundaries of what we think is possible.